might have occurred to you what a rocket actually is. Most people think of a tall and thin vehicle that launches into outer space. Well, this is not the whole thing. There are different types of rockets with various applications. The space rocket is one of them. Other examples are those used in military, fireworks, and etc. Despite having several kinds, they almost consist of same structural components. But today we'll be specifically analyzing space rockets. For hundreds of years, scientists have attempted to escape Earth's atmosphere. Now, with the invention of a rocket, it is quite possible to leave our planet. But what made physicists discover this ability? Well, it was all due to Newton's laws of motion. But before applying his rules, let's get familiar with the general mechanism of a space rocket. Like any other engine, fuel is burnt in the combustion chamber with the help of an oxidant, which produces a large amount of exhaust gases. Right after this process, the products are pushed out of the rocket through a nozzle that is specially designed for increasing or decreasing the speed of combustion fluids. Newton's third law tells us that for any action, there is an equal and opposite reaction. Therefore, the force pushing the exhaust products outward is the same one pushing the rocket forward. In physics, we call this force thrust. Be careful that the power generated by the rocket's engine must be huge enough to escape the pull of gravity, otherwise our mission fails. When the space rocket reaches the low Earth orbit, the fuel stored in boosters will be completely expended and these devices will be dropped down to Earth. As the rocket gets farther, the gravitational effect becomes more and more negligible. Therefore, at the absence of gravity, no external forces are exerted with the system of rocket and exhaust gases. As a result, it is possible to apply the conservation of linear momentum for this system. On the left side of this equation, we've got the first state where the rocket's mass equals m. But as the time passes a little, the stored fuel is combusted and the rocket's mass is reduced to m minus dm. In addition, its velocity increases to v plus dv. The other expression is the momentum of exhaust gases in the opposite direction with the absolute velocity of vx. In order to solve this equation more easily, we can rewrite vx in terms of relating velocity. Expanding the previous equation results in where the term dm times dv can be neglected since the product of multiplying two small quantities is much smaller than both of them. Now that we have a fundamental relation, we differentiate both sides with respect to time. According to Newton's laws of motion, the result of mass times acceleration equals the total force acting on an object, which in this case is the thrust force provided by the rocket's engine. At this moment, let us get back to the main equation where we had m times dv equals vx times dm. This relation actually shows us that any tiny difference in velocity is relative to a change in mass. So if we solve this differential equation just by separating the independent variables we've got, and we will end up with a velocity equation, where VO is the initial velocity of the rocket. Thank you all for your attention. Hope you have enjoyed watching this video. Leave us your questions down below, and as always, don't forget to subscribe.